So welcome you back to my class. And in my last class, we talked about few things like we talked about, discussed about groups, and then we talked about commutative groups, non-commutative groups. Then we talked about further cyclic groups. Also, we heard about few terms like order of an element. Okay, order of a group first, and then order of an element. We have seen few examples like Z plus is a group which is a commutative group, whereas S3 is a non-commutative group. Again, for infinite case, we have already seen GL to say R with respect to usual multiplication. That's an example of a non-commutative group. On the other hand, we have in my last class, we have already discussed cyclic groups, out of which Z plus is a cyclic group. And for finite case, we had heard about addition modulo n for some positive integer n. This group is also a cyclic group. So this is an example of an infinite cyclic group, and this is an example of a finite cyclic group. So hope you have already understood about this concept, because this is very important in case of many practical applications. For example, in cyber security. So this groups plays an important role for cyber security. So today we will also look after a few other groups. For example, in my last class, I also discussed about S1, which is nothing but some related to complex number. So all points on the circle, all points on this circle whose radius is 1. So this elements, any element should look like e to the power I theta, where I is nothing but the root of this polynomial. So I square equal to -1. Okay. So I is the root of this equation. So we have seen that if we consider all points, so if I consider say S1 to be the all points from the complex numbers, so it could be star also, that means non-zero complex number, such that mod of z equal to 1, then with respect to usual multiplication of complex numbers, this group also forms a group. Okay, this S1 also forms a group, and this is known as circle group. Circle group. Now I asked you a question that is S1 a cyclic group? So I asked you a question, is S1 a cyclic group? Till now, I don't want to give you any kind of hints. I just want to explore few of the things. You can search with this, just typing this word on the internet, and you will get plenty of such answers, and out of which you have to grab, or you can see few of the books through which you will get you the answer. But I am not going to tell you the exact things. But can you just give me some of the ideas how you are thinking about it? So somebody, can you please explain how you are looking at this example? So what is your intuition? Is it a cyclic or non-cyclic? Cyclic or non-cyclic? What is your intuition? Is it cyclic or non-cyclic? Somebody, please tell me. Is S1 cyclic or non-cyclic? What is your intuition?
The
Yes,
non-cyclic.
yes, very good. So your intuition is perfectly okay. Now you need to give me some rigorous proof. Okay. So some of, can anybody tell me a bit idea, not a whole, but some idea how to discuss or how to develop a rigorous proof for that? So what do you need to show? That there exists no G belongs to S1 such that G is a generator of S1, right? That you need to show. There exists no G such that G is a generator of this. Or if you can show that there exists some subgroup S1 which is also not cyclic. Okay, so that's you think on your own how to give some of the arguments here. So the idea is you need to show that there exists no G which could be which could act as a generator of this group, and if you can argue like this, then suddenly S1 it cannot be a cyclic group. But S1 has a strange feature. For example, if I ask you the question is there any group, any infinite group having finite subgroup? Okay, so the first, maybe many of you have some idea about subgroup, but many of you may not have any idea about subgroup. So today we are going to discuss about this question. So I need an infinite group G. It should be infinite, but it should have a finite subgroup. So the first question is, what is a subgroup? So what is a subgroup? Okay, so sub and then group. So from the name itself, you can understand that subgroup must be a kind of group. So subgroup means it must be associated with some original group. So there must be some original group, say G star is my original group, and suppose S is my subgroup. Okay, say S star. What does it mean? So let G be a group, say G star be a group, and S be a non-empty subset of G. Then S with respect to the star with restriction. What does it mean? So you have already encountered with the restriction of a function. As I mentioned, this is a binary operation. So it must be a তুমি অনেক দেরি করে ঢুকলে, so you are little late. Okay, so as I mentioned, this star, this is a binary operation, and star one is also a binary operation. So star means it's a function from G cross G to G. Now look at S is a non-empty subset of G. So S is a non-empty subset of G. Okay. Now if I restrict my star to say star one from S cross S to S. So see, it's a restriction. So all the elements are not coming from G but coming from S. That's why it's a restriction. You might have heard about in your analysis class the restriction of a function. So here this is a restriction. If this, then this is called a subgroup, called a subgroup of G if S with respect to the star one, which is nothing but exactly the star which is restricted on S, this is itself a group. That means on its own right, if S with respect to this restricted operation, sometimes when you are matured enough, we will not write it as star one, but instead we shall use the same star as subgroup. Okay. For example, suppose we consider Z plus, and if we consider 2Z plus, as I mentioned, we are going to use the same operation, not star one or star bar something, same operation plus. Now the question is 2Z a subgroup of Z? First of all, please try to look at, without looking at Z, please have a look at 2Z. And if I ask you the question, is 2Z plus a group? Is 2Z plus a group? What is your answer? Yes, because if you add any two even integers, that will also be an even integer. And 0 is also within this 2z, and the inverse of some integer, say 2n, is the inverse will be minus of 2n, right? And associative property is also there. So associative is a hereditary property. Since it also happens with z, it must also happen with 2z. So at the end, what we can talk about, we can say that 2z plus is a group. So you can understand that 2z plus itself a group on its own. That means you don't require any other things. As a result, you can think of this plus is same as this plus, or you can think of this as a restriction of plus to this 2z subset. And also 2z is a subset of G. So all the properties of this are satisfied. So 2z is a subset of Z, and this restriction, this plus, is itself a group on this 2z. As a result, 2z is a subgroup of Z. Now the question is, sometimes it may be difficult to understand whether a group, a subset. So suppose I give you a question like this: let S be a non-empty subset of G. Okay. How can I check? How can I check? How can I check whether S with respect to this restriction, say G star 1, or sometimes we will delete this 1 and we write star, is a subgroup of G. So is there any easy method? Yes, there is an easy method, and that's an if and only if condition. And it says that let A B belongs to S, then S with respect to star is a subgroup of G star if and only if for all AB belongs to S, A B inverse must also belongs to S. Okay, that means if we consider, so this is an if and only result. Mind that it's very strong result. How to check? Take any for all. It should not be like for 1 2 elements it happens, but it should be for all AB belongs to S, A B inverse must also belongs to S. And this proof is quite easy. I request you to have a look at from any book. So you may follow my book, or maybe Gallian's book, or Malik Mordeson book, or Dummit Foote book, any book. So you'll find the result, the proof of this result. So I'm not going to the details of this proof, but that is very important result. Now consider, I will just check how it happening. Say S, I consider S3 group. Okay. Now I consider H to be say E and 1 2 3. So E and 1 2 3 cycle is there. Okay. Now my question is S a subgroup of S3? What is your intuition? Yeah, true or false? What is your intuition? Is it true or false?
False.
Okay. Somebody says false. Okay. Very good. The answer is surely false. Why? Take any two elements. Say I have taken my A to be say 1 2 3 and my B to be say E. And let us check whether A B inverse belongs to S or not. So what is A? A is your 1 2 3, 1 2 3, and E inverse is again E. That means 1 2 3, and that becomes belongs to S. But that is not all. So if you find some AB such that this property is satisfied, then you may not be that satisfied to say that that is a subgroup, but it should be checked for all such elements. Okay. Now if I consider A to be 1 2 3, and if I consider B to be also 1 2 3, then we can check that A B inverse equal to 1, 2, 3 into 1, 3, 2, right? What is this value? What is this value? Quickly. 1 goes to 3 and 3 goes to 1. So 1 goes to 1, 1 is gone. Then say 2 goes to 1 and 1 goes to 2. So 2 goes to 2, okay? And then, and then, so what is happening here? Now, how will you prove or disprove that? So you can see that this is E because I have taken A and B was the inverse of A itself, right? So A and B were taken from S, and I have checked that A B inverse is this, and that is E, that is also S. So again, this property is also satisfied. Now tell me how to prove that this is not a subgroup. How will you prove with this result? Tell me.
Sir, A square is not in the set. S.
Okay. So how will you show it? By using what I am saying, that using
That
this something take as A and something take as B.
that take A as E and B as 1, 2, 3.
Very good. Take as A as E and B as 1, 2, 3. Very good. Then A B inverse. This should be E into 1, 3, 2, and that is equal to 1, 3, 2. But 1, 3, 2 is not within S. So you fail with this E and this A and this B. Now you can understand that with this result, you can say that if it would be a subgroup, then it should be true for all AB. So I have taken this A and this B, and then we found that A B inverse is not within S. As a result, we can directly say from this result, which you need to prove, that S is not a subgroup of S3. Okay. Whereas if I consider my S to be say E12 and check with this result whether that is also there or not, then you will able to find that for all AB belongs to S, A B inverse is also belongs to S. That will imply E12 is a subgroup of S3. Okay, that you can check on your own. So that's a very strong result. Okay, now let me ask you one simple question. So you have heard about Z and you have heard about, so Z plus, you also heard about the group Q plus, and if, sorry, Q plus. So if I draw like this, then this is my Z and this is my Q plus. Okay. Now, is there any subgroup of G is there which is properly contained, which lies in between? That means, can you find some G which lies exactly within these two groups? Is it possible or is it not possible? So question is, does there exist any such G? Yes or no? If yes, give me. If no, why no? Is the question clear? I need to find some subgroup, additive subgroup of Q plus, which is strictly bigger than Z plus. Is it really possible or it's not possible? If it is possible, tell me why, and if not, then also tell me why. So any idea? Anybody? So you heard about many things, but you haven't thought about this question, right? You know many groups, but why not in between any groups? So anybody? Let's see. So what is your intuition? Let me check. What is your intuition? It should be true or false. Any intuition, any guess?
Sir, false.
False.
Yes, sir,
According to you,
false.
means there exists no such group, right? According to you, no. You
Yes,
mean
sir.
to say no or yes?
Sir, no.
So you mean to say no or yes? Yes or no? Which one? Two. No. So most of you think that there exists no such group. Okay, very good guess, but let's check. Okay. So yesterday we talked about cyclic group, right? So we know that if G is a cyclic group, then there must be some generator G, and if G is an additive abelian group, means additive group, then any element, take any element X belongs to G, then X can be written as, how X can be written as in an additive group with respect to G, some something like G and then some n into G, where n belongs to some integer, right? Is it correct? So if G was a multiplicative group, then this same thing would be X to be G to the power n for some n belongs to Z. So here we are talking about the additive group. That's why for the time being we are not considering this. Okay. Now tell me, if I consider half, is half within Z? This does not belongs to Z, but half belongs to Q, right? Now if you consider what is the subgroup generated by half, let me give the idea. What would be the form generated by half? So half belongs to Q, and if I consider half, the group generated by half, first let me give me the elements, then it will be quite easier for you to understand. Suddenly half will be there, then who else? Who else?
1.
1 will be there, then
3 by 2.
3 by 2.
3 by 2, then
2.
2.
2 will be there, then
Sir, 5 by 2.
okay, and so on, right? 5 by 2 and so on in the positive sense, and then some negative numbers. So negative all everything. So minus half, minus 1, minus 2 by 2, minus 2, minus 5 by 2, and so on. And anything else? Anything else? Most important term you missed.
Sir, 0.
0. Okay. So they are all the elements. Now from the construction, this is a group generated by whom? Generated by whom?
1 by 2.
Generated by half. Now suppose this is my G. Now, of course, Z is properly contained in, sorry, G is properly contained in Z because half is not within Z, but half is with G. And suddenly, one third is not here, but one third is in Q. So, Q. Any problem with understanding that? So, apparently, you thought that your answer was no, right? But it's not the correct answer. The answer should be yes. And now you can understand, you can construct infinitely many such subgroups which is in between Z and Q. Can you tell me any other subgroup which is within this range?
The subgroup generated by 1 by 3.
1 by 3, very good. Now, if you ask me this question, this is, how do you write or like? So, this is your Q, this is your Z, and suppose this is your, so this is your, say, ideal generated by half. Now, can somebody be able to tell me how should ideal generated by 1, 3 will fit here? So, if I ask you the question, which one is bigger? Is this is a subset of one third, or half ideal generated is bigger than one third? What would be your answer? What would be your answer? Who is bigger?
So generated by 1 by 3.
So generated by 1 by 3 is bigger. So can you write half in terms of, so according to you, half must be within 1 by 3 then? Can you write this in terms of this? If so, then half should be written in terms of n into one third. Then what would be the value of n? The value of n will be 3 by 2, a contradiction, right? So if half will belongs to 1 by 3, then half, then suddenly the subgroup generated by half will also be a subset of 1 by third, according to you. So according to you, 1 by 3 is bigger than this. So according to you, this is correct answer, right? According to you. But if that is the case, then half will suddenly be within the subgroup generated by one third. So if half will be here, then half must be written in terms of the generator, as just now I have mentioned, it is an additive group for some integer, z, for some integer n. In that case, n will be of this form, but this is a contradiction. This cannot be a form of 3 by 2, can never be a form of n integer. So we get a contradiction. So conclusion is this is not. Now what will be your conclusion? Is this is correct? Is this is correct?
No, sir.
So this is also not correct. Like here, this is not correct. This is not correct. So what is happening here? So in case of natural number, you might have heard about the law of trichotomy. You heard about the term law of trichotomy? Law of trichotomy. Have you heard about the law of trichotomy? That means if you take any two natural number, it is also true for Z as well. It says that either A is less than equal to B, or A is greater than equal to B. So any one of the relations may happen. Either A is equal to B, or A is strictly less than B, or A is strictly greater than B. So for any two integers, one of these relation must have occur. But here this relation is not like that. So this relation it might happen two subsets may not be having this relation. So they are not actually equal, or no one is a subset of others. Okay, so it's a quite interesting relation. So that means we can say that these two subgroups, or as a set, they are not comparable. So again, that's very important with respect to this subset. So in case of less than equal to, in case of integers or rational numbers or real numbers, you can have this relation. But in case of a subset, you cannot have. Again, for example, in case of a complex number also, you can never say that a plus ib is greater than c plus id. So there is no such relation unless you define something way. So you may define and kind of ordering, say for example, this will be greater than if and only if mod of a plus ib greater than mod of c plus id. Okay, in that way you can induce it. But in a normal sense, we say that 2 is less than 5. In that way, in complex number, you cannot define a kind of ordering unless you define in a forceful manner. Okay, that means the normal ordering is not preserved in case of a complex number. So you cannot normally say that 2 plus 3i is greater than 1 plus I. You cannot say like this because this ordering is not valid in case of complex numbers. So it's a again very interesting topics, but I am not going to that. But you must read all those things in your undergraduate first year, at least in your first year undergraduate level, you might have heard about all those things. But if not, then again go through this. Just search for law of trichotomy and what does it mean and how the relation works. Then you will get all the detailed information. Okay. Okay. So we were where we were somewhere like that. So we can find now infinitely many subgroups of this. Okay. Now come to my this question what I asked you earlier, that is there uh, so that was is correct, right? It is yes. Now before that, what I asked you the question, uh, the question from where I started. Okay, is there any infinite group having finite subgroup? So is there any infinite group having finite subgroup? So just have a look at this question. Is there any infinite group having finite subgroup? So I'm just restating this statement. Is there question is there is there any infinite subgroup, sorry, infinite group having finite subgroups? What will be your answer? So the group has to be infinite and it must have some finite subgroup.
Yes, sir.
Okay, example.
Sir, if we take the group as circle group and take the subgroup as in root of unity.
Okay, so suppose you consider the third root of unity. Third root of unity. That means the elements are 1 omega omega square. Okay, so this is an infinite group. So how the image looks like geometrically, that representation is also very important to know more about abstract algebra. So this is my S1 circle group, the whole points on that S1, and how the 1. So here in S1, can you tell me how they look like? 1 omega omega square. So there are also 3 points on S1. How they look like? Can anybody tell me? in a complex plane, how do you draw or how do you plot the 3 points on this complex plane? Somebody tell me. Okay, do you know what this point represent?
Sir, 1 point will be will make 60 degree with the x-axis, and another one is 120 degree with the x-axis.
Okay, somebody says this is 60 degree and another point is 120 degrees. So this is 120 degrees. Say. Okay, do you agree with this, his argument, or you want to put something else? But he has given a nice guess. Okay, anybody? Okay, suppose this is my 1 and this is my omega and this is my omega square. Okay, so every time it makes an angle 60 degree. So first 60 degree and then 120 degree. Now somebody tell me what would be omega into omega square. So first forget about the geometrical representation. Just give me the analytical answer. What is this value? Omega into omega square. What should be this value?
1.
It should be 1. That means omega into omega square. First see that once you multiply 1 into omega, it gives you omega. That means a 60-degree rotation anti-clockwise. Again, when you have omega into omega, it gives you omega square. Again, a 60 degree, that means 60 plus 60 degree, that becomes 120 degree. And it comes here. Now, when you are making 1 omega omega into omega, that is omega cube, that should be my 1. And that should be, according to your definition, it should come here. Again 60 degree. That means 180 degree. And it should represent 1. But that is not the case. Now restate your
Sir,
answer.
e to the power 2 pi by 3 and e to the power 4 pi by 3.
Okay.
120 degree and
So what is 2 pi by 3? Can anybody in degree?
sir,
What is this
240,
value?
240
120 or
degree.
240.
120
Yes.
or 2.
So now you can understand. So not always it's possible to understand things analytically. So sometimes geometry gives you a very nice hints. So if you think about it, now you can cross check or verify yourself. Okay. Now it's quite clear to you that it should not be. So 1 should come here. It's true that it should be 1, but the omega should come here 120 degree. Okay. So this should be 120 degree and this should come here and that should be 240 degree. So this is my omega and this is my omega square. Now if you again multiply with some omega, it will become 1 here because again 120 degree, that means 360 degree. As a result, it will come back to 1. So now geometrically it's quite clear to you how omega square. Now quickly, can fourth root of unity, say 1 fourth root of unity, if I write like lambda square lambda cube. Suppose
Sir,
this is my g.
980,
Yes,
180
very good,
into 270.
very good. So this is my 90. So this is my 1. So this is my 1. Sorry, this is my, this point is my 1. This is my, say, lambda. This is my lambda square, and this is my lambda cube. Okay. Now, if somebody wants to write like 1 I, say I square is minus 1 and I cube is minus I. Okay. So you can understand that this is nothing but this. So this is 1 and this represent I. This represent minus. So how much is this represent?
Minus
So
1.
this is minus 1 and this is my minus I. Okay. Now it's clear to all of you. So this is the fourth root of unity, which is nothing but 1 I square means minus 1, and then I cube means minus I. So I cube, why I cube is, so I square into I square is minus 1, so minus I. So this value. So now geometrically you can have a nice structure what you should learn in your complex uh, complex analysis part. Maybe you have been already taught in your undergraduate level semester 1, but still I think now it's better. I mean, it's clearer to all of you to understand how the groups of units looks like. But now you can understand this answer is obvious. So there exists an infinite group having finite subgroup. Okay, but please, the first idea of any subject is try to think from a very scratch, not from a very hard level. So as you know, any group has a subgroup always. E is always a subgroup. Okay, take any group, and if you consider E, then this is always a subgroup. If you consider G, then G is again a subgroup of G. So these two groups are always happening for any group. And this group is always a finite group. So if I ask you this question, then obviously this question answer is yes, because take any infinite group and then consider E. Then that group will always have a finite subgroup. So take any infinite group, doesn't matter, and then consider E, and your answer is always yes. But if I ask you any no having non-trivial, so these groups G and E are called trivial subgroups. They are called trivial subgroups. Trivial subgroups, among of which this is not a proper subgroup. So proper subgroup means the subgroup which is properly contained. So this is not a proper subgroup. Proper subgroup. So few new terms are now added with your vocabulary. So it's a trivial subgroups. That means D and E are called trivial subgroups. Proper subgroups mean which are properly contained in G. For example, E is a proper subgroup, but G is not a proper subgroup. So if I ask you this question, any infinite group having non-trivial finite subgroup, then your answer could not be start with any G and E. Then that E will become a trivial subgroup. So in that case, this example that somebody has already given, so consider G to be my S1 and consider S to be my this, say 1 omega square, any nth root of, so here in I have taken, so nth root of unity, root of unity. So in that case, n is my 3. If you consider n to be 4, then this subgroup becomes 1i minus 1 minus I. Okay. So if you take n to be 5, then fifth root of unity and so on. So now you can understand that this group has, this is an infinite group. S1 has is an infinite group, but it has still plenty of finite subgroups. Now if I might ask you this question is an infinite group, but so infinite non-infinite group, okay, infinite group having finite non-trivial cyclic subgroup. Can you give an example? So the group is infinite but having finite non-trivial cyclic group, because E is a trivial cyclic group. It's generated by E itself, right? So E is generated by E. So this is a trivial cyclic group. Can anybody tell me any infinite group having finite cyclic subgroup, which is non-trivial? Somebody quickly.
Sir,
Group is
cube roots of unity, and which is just
very good. The same example. See, this is a very powerful example through which you can construct many of the questions which are usually asked in some of your competitive exams. So this nth root of unity or S1, or I will teach you more, then you will find that you will have plenty of such questions that could be asked or that could be answered if you have a nice and solid background or solid understanding about this kind of simple groups. So they are simple. Again, simple is again a technical term in our abstract algebra. There is a group called simple subgroup. So I will simple group. So I will talk about this group later on. But till now, is it okay with all of you? Okay. So again, let's have Z say 10 plus. Okay. Now I construct a subset like 2, 4, 6, 0 and ask you the question, is S a subgroup of Z10? What would be your answer? Is S a subgroup of Z10? By any means. You know now many things about group theory and subgroup.
No.
So this is
Why
not a
not?
group. The 2 plus
The,
6 equals to 8 is not present in this group.
very good. So it's no. And why this is no? As you mentioned, the 2 plus 6 is 8, and that is not within S. As a result, this can never be a closed subset, because closed in that sense, closure property doesn't satisfy here. So S plus can never be a group. So as I mentioned, that by its own it should be a group to have a subgroup. Okay, so the answer is no. Very good. Okay, now let's come to another important aspect, that is, so we talked about Zn plus, right? Now if I just switch Zn dot with respect to usual multiplication or modulo n. So if I ask you the question, is Zn dot a group, what will be your answer? True or false? Zn with
sir,
respect to
it
dot.
must satisfy some properties. Then it should be a group. Actually, if I take uh, yes, sir. It may be a group by some property
Okay, so you say that if you choose n properly, then it may be a group.
no, sir. Actually, if we take A from this group, and if the GCD of A and N is 1, then it should be a group, actually.
Okay, so take say Z6 and consider 5.
Yes, sir.
Then GCD of A and 6 is 1. So then you say that that implies Z6 with respect to dot a group, according to you.
Sir, actually, its elements are 1 bar and 5 bar,
Okay,
and
so what
this
you
is
told
actually the
is
group.
perfectly correct, but that should not be Zn with respect to dot. That should be Zn star. Okay, I understand what you want to mean.
Yes, sir.
I
Actually,
actually,
When n is prime,
yes, then it will be a group.
Sir,
Okay,
if n
let's
is
see.
prime, then all the elements 1, 2, 3, and n will
No, what is there in Zn, Z7? It consists of
all the
0.
elements 1, 2, 3, 4. Sir, yes, we should
Yeah,
eliminate
also
0.
eliminate 0.
So all the element except 0. So that means that is not. So first answer is Zn with respect to dot is not a group. So it is false because Zn contains 0 element, right? So Zn contains 0 element, but you cannot have a multiplicative inverse of 0 in Zn. So it cannot be a group. As a result, the answer is false. So you just take out of this element Zn minus 0. And if I ask you this question, is Zn minus 0 a group with respect to dot? What would be your answer? True or false?
False.
Why false? Okay, yes, it's false. Suppose let's take another example, say Z6 minus 0 with respect to multiplication. Okay, now consider class 2. And if I ask you this question, what is the multiplicative inverse of class 2 in Z6 minus 0? What would be your answer? You will not find any of such x from this group whose multiplication will be class 1. There will be no such x. As a result, you cannot find the multiplicative inverse of 2 in Z6 minus 0. So again, it will fail to be a group. That's why this is false. Now, in my last class, I have already mentioned those elements which are relatively prime to n. If you just consider them, so sometimes we write it like Zn star, or some of the authors they write it Un. So that is known as group of units. Group of units of Zn. So which elements are there? All such elements belongs to Zn such that GCD of A and N equal to 1. So you consider all such elements in Zn and then consider multiplication. Then this forms a group, and this is true. For example, suppose you have Z20 star. That means U of 20. Now tell me how many elements and who are the elements? So 1 should be there, 2 will not be here, 3 will be here, 4 will not be here, 5 will not be here, 6 not be here, 7 would be here, 8 will not be here, but 9 will be there, 10 will not be here, 11 will be there, 12 will not be here, 13 will be there, 14 will not be here, 15 will not be here, 16 not, 17 will be there, 18 will not be here, 19 will be there. So altogether 2, 3, 4, 5, 6, 7, 8. Now, as I mentioned in my last class, what would be the cardinality of this? That means all such elements which are relatively prime to n, and that is nothing but phi of n. That means phi of 20. What is phi of 20? Quickly, can you tell me what is phi of 20?
8.
8.
Yes. So cardinality of this set exactly. So this is 8. So now from Zn, we have now constructed Zn star or Un, which is nothing but the group of units of Zn, which are this set. And cardinality of this set is phi of n, that is depending on that n. Okay. So this group is also very important. Now I will show you very interesting observation related to number theory. Okay. The observation is how to calculate this phi. If I ask you this question, what is phi of 7? What is phi of 7?
6.
6.
6, 6,
What is phi of 11?
10.
10.
10.
10.
what is phi of say 101 is a prime? What is this?
100.
So in general, if I write phi of p where p is prime,
P minus
then
1.
it should be p minus 1. Very good. Now I will give you another observation. What is phi of p to the power n? Okay. What is phi of p to the power n? Okay. That means all such numbers, all such x. So you want to find the cardinality of all such x which are positive integer, of course. So 0 strictly less than x strictly less than equal to p to the power n, such that GCD of x and p to the power n equal to 1. So you want to calculate the cardinality of this set, right? So let's just take in a other way. That is, I want to count the number of elements in say G equal to 0 less x less than equal to p to the power n, such that GCD of x and p to the power n not equal to 1. So I want to calculate the number of elements x such that GCD of x and p to the power n is not equal to 1. Mind that here p is my prime. P is a prime. Can anybody tell me how to calculate what is the characterization of this x? X has a peculiar and particular property. What does it, extra property does x has? Such that GCD of x and p to the power n is not equal to 1. Those elements which are not relatively prime to p to the power n. So that means x must have some special property. What is that x property? Can anybody tell me what is that property? X must divide p to the power n, or you are very close but not yet. So x and p to the power n does have some property. So x must contain something as a factor. Can you tell me what? X must contain
Sir,
something as a factor. What is that? Yes.
P.
Sorry?
P.
P, exactly. So here x must have P as a factor, right? So how the x looks like? Some P into K, right? Where from where this K varies. So 1 less than equal to K and less than equal to how much? This is important. How much? So x as a factor, sorry, p as a factor. So I have written p into some
p
k.
to the power n minus 1.
Very good. So it should vary from p to the power n minus 1, because if it is p to the power n minus 1, then x becomes p into p to the power n minus 1. That means p to the power n. Okay. So how many such x exist? How many such x exist? From here it's clear. How many such x exist?
P to
It
the power
depends.
n minus.
p to the n
Yes,
minus
very good. It depends on k. For different k, you will have different x, because this part is fixed. And how many such k are available? So it varies from 1 to p to the power n minus 1. That means there exists p to the power n minus 1 many such k. Okay. And there exists p to the power n minus 1 such x. Such k varies means such x varies, right? So they are all elements which are not relatively prime to p to the power n. So if I ask you, so there were p to the power n many elements, and these many elements were not relatively prime. So now tell me, what is p to the power n? Tell me now in terms of p
P
to
to
the
power
power
n,
p to
P
the
to the
power
power n
n were the total number of elements, then
minus P to the n minus 1.
p to the power n minus 1. Great. So this is the formula for p to the power n minus 1. Now if I ask you this question, what is phi of 16? One can very easily calculate it by just cardinality of this, like 1, then 3, then 5, then 7, then 9, then 11, then 13, and then 15, right? 1, 2, 3, 4, 5, 6, 7, 8. And just check by this. So 16 means pi of 2 to the power 4. And that is nothing but 2 to the power 4 minus 2 cube. 16 minus 8, that is 8. The same as 8. Okay. But for 2 to the power 16, it's easy to calculate it by hand. But if I ask you this question, pi of 2 to the power 100, then it would be really difficult for you to calculate by hand. But now it is very easy. 2 to the power 100 minus 2 to the power 99. That means if you take 2 to the power 99 common, then it will be 2 to the power 2. So this is minus 1, that is 2 to the power 99. Now it's very clear and very easy for you to calculate if you have this formula. Now I will just mention it now, but when I will go further, I will give you uh, more answer, like the proof of this, like if a and b. So what is the value of phi of a and b? This value is phi of a into phi of b if GCD of a b equal to 1. Okay, that means what is this value of, say, 35? Quickly tell me, what is this value of phi of 35? Then phi of 7 into phi of 5, because 7 into 5, a b, they are relatively prime. So this is 6 into 4, that means 24. Very easily now you can calculate. Understood? Any doubt? So this proof I will let you know maybe at the end of the course, because when I will have, so there are number theoretic proof, but I will give you a very simple proof based on cyclic groups, property. So maybe after a few classes I will able to describe you the proof of this. So that's a very simple proof by using number theory, but that is much bigger. But if you apply the group theoretic technique, then your proof is very easy. Maybe within 3 or 4 lines you will able to prove this, but you need to apply few of the results of group theory. Now can somebody tell me what is this value? Pi of 100 is how much? Quickly, let's see who give you the first answer. Pi of 100, tell me quickly.
90. 90.
90.
90. 90.
Yes,
Okay,
sir.
let's see. How did you get this? Pi of, how did you get this?
The 10 squared.
10 square.
Sir,
And
I
then,
think it's 40.
okay, somebody says 40. Good. And then 10 square. Then how did you use this?
The
10
10
square
minus
is,
10.
so you forget that P was, what was your P? P was, P is a
Prime.
Prime.
prime number. But your 10 is not a prime number. So this is valid only for prime numbers. But you can suddenly use this result. So first try to break, instead of doing that, try to break like this. Phi of in terms of product of primes. So it's 2 square into
it's 40.
5 square, right? So this is 2 square into 5 square. It's a product of primes. So it's 25, it is 4. So 100. Now use this. So your A is this and your B is this. Look at this. A and B are relatively prime. I never tell you that AB are prime integers, but what I say that GCD of AB equal to 1. So here what you see? Here you see that this is 4 and this is 25. Their GCD is 1. So very well you can write 2 square into 5 of 5 square by using this result. Now you can use this result, okay? Because now 2 is prime, 5 is prime. So it's 2 square minus 2 and it's 5 square minus 5. 2 square minus 2 is 2 and 5 square minus 5 is 20. So 40. So 40 is the correct answer. Is it clear to all of you? And in many question of JAM question paper, you will find similar question. Not exactly. There are many other things through which you will have to calculate phi of n. And many questions that they are asked is to calculate. Now, if I have already mentioned you, but I have not given you the formal proof. I told you to read the formal proof. For example, if I consider say Z200 plus, so is this a cyclic group? Is this a cyclic group? True or false?
True.
Is this is true? Now that means it has some generator. If I ask you how many generators are there, how many generators are there for Z200 plus? Very quickly, can you somebody give me the answer? So what you need to know, basically all such elements which are relatively prime to 200 are generators, right? In my last class, I have already explained, but I have not given you the proof, but you should have a look at the books where you will get the proof. The proof is not that difficult. So
Sir,
how many,
80. 80.
okay, somebody says 85 of 200. Let's calculate. That means 5 of 2 cube into 5 of 5 square. And 5 of 2 cube is how much? 2 cube minus 2 square. And this is, sorry, 5 square minus 5. And that value is 4 into 20, and that gives you 80. Very good. Now you understand the whole thing. And this formulae are quite easy to understand, but it's very important. Unless you have this idea, you won't be able to calculate in exam very quickly. And the proof is also not very difficult. I may come to the proof of it maybe within 3 to 4 classes when I will go more details about cyclic group. But this part you need to read from a book. So I'll give you as a homework the proof of this, formal proof of this, that uh, let Zn plus be a cyclic group of order n, then class A belongs to Zn is a generator of Zn plus if GCD of A and n equal to 1. So you can put it as if and only if also. So if GCD of n equal to 1, then that will be a generator, and if this is a generator of Zn, then the GCD of n will be 1. So that you need to prove from a book, any book, wherever, whichever you feel or whichever you find it. You just have a look at this, and maybe in the next class I will ask you the question, okay, in the Viva. Okay, it's clear? Okay. Now let's come to another issue. So there is another very interesting thing. So we have Zn plus For example, take uh, say Z6, and we have seen that in Z6, class 1 and class 5 are the generators. Now, if I ask you the question, what is the order of class 1 in Z6? What is the order of the class 1?
6.
6.
6.
What is the order of class 5?
6.
6.
6. So, the idea is in a finite cyclic group, the order of the generator is same as the order of the group. Is the statement clear? For a finite cyclic group, the order of a generator is same as the order of the group. For example, here, so this is a finite cyclic group of order n, here n is 6, and the order of the generators are all 6, same as the order of the group. I ask you this question, is the same result true for infinite cyclic group? True or false? What do you think? What is your intuition?
Sir, the order of the generator will be infinite, so we cannot say two infinities are equal. Like,
Okay. So, yeah. So, in that case, so in case of infinite cyclic group, one example is Z plus. Okay. The order of the generators of R1 and -1. So, their order is infinite. Infinite. So in that way, I mean, in that way, you can say that this is also true. Okay. So in case of infinite cyclic group, you have only seen for Z, but there could be many other infinite cyclic group. Can you give me another example of an infinite cyclic group? Quickly, you know, another example. So this is an infinite cyclic group. Another example of infinite cyclic group. Okay, from Z, can you construct some infinite cyclic group?
NZ.
Say NZ.
What is N? If I put n equal to 0, then will that be an infinite cyclic group?
No, said n belongs to natural number.
N belongs to natural numbers. So when you say some statement, we need to think about in a detailed way. Okay. So your answer, what you thought about was exactly perfectly okay, but what you explained have some gap. So for n equal to 0, it would be a problem. But if you from n belongs to n, then it's fine. Okay. So 3z. 3z is again an infinite cyclic group. So who are the generators in case of z and 3z?
3.
3 and -3 also. Okay. So now you know that you can construct infinitely many cyclic groups. Infinitely many infinite cyclic groups. Now if I ask you this same question, can you have any other type of infinite cyclic group? What you have already I taught you today. Another example of infinite cyclic group. Quickly. Another example which are not of this form. And I have already taught you. Anybody?
So Zn plus.
Now you remember. Zn plus is a finite cyclic group. So the subgroup generated by half, it contains infinitely many elements. You wrote all the elements. So plus minus half, plus minus 3 by 2, plus minus 5 by 2, and then 1, 2, 3, all 0. So this is generated by half. So again, you can see that the order of this element is infinite. So as I mentioned, this is true for finite, and if you consider the infinite cyclic group, then you will also, the result is also true. Okay, so it's not only for finite, for infinite cyclic group. If I consider, okay, some of the authors, as I mentioned, that they put the order of the generator or order of the some element is infinite, they sometimes say that 0, the order of that element is 0, but most of the authors, they put it like this, infinite. So that's why some of the authors, they consider this to be in a separate way. If you consider that order of say 1 is infinite, then your idea is this is also true. But if you follow the notion that order of 1 is 0, then this is not true. In that case, this is finite, but this is infinite. So this is little bit depends on how you are tackling your problem. But in our case, we'll consider the order of 1 is infinite. As a result, infinite cyclic groups order and the order of the generator is exactly the same. Is it clear to all of you? Okay. So you have already had many of the infinite cyclic groups. Clear? Okay. So this is generated by half. Similarly, you can also generate it by this. Now tell me which one is bigger as a subgroup. So both of them are subgroup of Q plus, right? Now, this one is true or this one is true or may not be comparable.
Sir, 1 by 4 is bigger.
1 by 4 is bigger. Okay. Any others? That means according to you, this is true. Sorry. Yeah. This is a subset. According to you, this is correct, right? According to
Yes.
you. So what do you think? So everybody thinks like this. 1/4, the subgroup generated by 1/4 is bigger.
Yes, sir.
Okay. Why so? So what are the elements in 1 by 4? So like this 2 by 4, and if it is 2 by 4, then automatically half of the element is bigger. Okay, but 1/4 can never be an element of this. So clear. Now it's clear to all of you. Very good. Okay. So in my next class, what I will do, I will talk about another very important term that is known as normal subgroup. So already we have talked about subgroup. In the next class, I will talk about another important term that is known as normal subgroup. So I request you, all of you, to read from any book or from internet the part till now what I have explained, that is group, then subgroup, examples, then then order of the group, order of the group, and then commutative, non-commutative, and etc. So there are plenty of examples I have already explained, and there are plenty of examples are there in your books or in internet. So please have a look at this just before normal subgroup, whatever are there, you do that. Also, I talked about cyclic groups. Cyclic groups. So usually you will find cyclic groups may come after normal subgroup, but I have changed the ordering. I first given you the idea about cyclic group, and then I will talk about normal subgroup. But in your book you might have the this as a subsection that will come earlier than cyclic group. But also read about this cyclic group, the results related to cyclic groups. And then we will do lots of problems from here that usually come from JAM exam or some NBHM or TIFR exam. And that will give you some idea about more about the groups. So unless you do lots of problems, the whole concept won't be very clear. You won't be able to do only theoretical things, and you can never have a very good idea what are the things, and what try to think geometrically if it is possible. Not always that you will able to understand geometrically, but for example, if I ask you this question, suppose I started with a square. Okay, suppose assume that this is a square, and I want to construct all possible symmetries. So my G will be all possible symmetries, all possible symmetries. Symmetries means you already know because we already done it for equilateral triangle. Symmetries on the square. Now can somebody be able to tell me what could be this group look like? Okay, let's start with this. Maybe it may take some more space. Okay, say I start with a square. Say write it 1, 2, 3, 4. And if I apply E on it, what I will get? I will get 1, 2, 3, 4. Okay. Then I do it a rotation by how much angle to have a symmetry? Rotation, how much angle?
90.
90 degrees.
90 degree. Very good. So I put it 1, 2, 3, 4. What I will get? I will get 1, 2, 3, 4. I will get 4, 1, 2, 3. So as a permutation notation, how do I write it? 1, 2, 3, 4. So if I write like this, 1 goes to 4, 2 goes to 1, 2 goes to 1, 3 goes to 2, and 4 goes to 3. Okay. So this is my notation. So you can change the other way around. Anything that you like. Okay. So the my next would be I start with a rectangle. So 1, 2, 3 rotation. Now I will get 180-degree rotation. So if I put 1, 2, 3, 4, and after that, what I will get? I will get 1, 2, 3, 4. The 4, 1 and 3 will come here, and then 4 will come here, 1 will come here, and 2 will come here. So cyclic notation wise, 1, 2, 3, 4. So 1 goes to 3, 2 goes to 1 goes to 4. Yeah, 2 goes to 4, 3 goes to 1, and then 4 goes to 2. Similarly, I can have other rotations as well. I can have 1, 2, 3, 4, 1, 2, 3, 4. If I move to an angle, how much? How much angle? So 1, 2, 3, 4. How much angle shall we?
270.
So 90. it was 180-degree rotation, right? 180 degree. So it's 270, right? So then what will come here? So 270 means what will come here? Anybody tell me what should come here?
Say 2,
2. Then here
3,
3,
4, 1.
4, 1. So notation wise 1, 2, 3, 4. So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. And then if I have rotation, so if I write it like it's r, then r square, and then this is my 270-degree, this is my r cube. Okay, then any other symmetry that you can find? So
Only
this,
about diagonal.
okay, flip around diagonal, so that may also happen, or this may also happen, right? So flip around this and flip around. So if I write it 1, 2, 3, 4, then 1, 2, 3, 4. Then if I flip around, say this one, I call it F1. So what will happen? It will look like 1, 2, 3, 4. It will look like 2 will come here, 3 will come here, 1 will come here, 4 will come here. So notation wise, 1, 2, 3, 4. So 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. Okay, so I call it F1. Similarly, you could have F2. So like this, if we have F2, so this is my F2, 1, 2, 3, 4, 2, 3, 4. So it should look like 1, 2, 3, 4, 4, 3, 1, 2. And permutation wise, 1 goes to 4, 2 goes to 3, 3 goes to 2, 4 goes to 1. Okay. Any other? Any other? Any other symmetry?
Diagonal flip.
Very good. So I can have, say this is my F3. So if I rotate like this, so it becomes, these two will remain fixed. That means 2, 4, and this will be 3, and here it will be 1. And that is nothing but, so I call it F3, and that is 1, 2, 3, 4. So 1 goes to 3, 2 goes to 2, 3 goes to 1, 4 goes to 4. Similarly, I can have another diagonal. Sorry, this diagonal. So 1, 2, 3, 4, 1, 2, 3, 4. Here 1 and 3 remains fixed. So here 2, 4, and we call it say F4. So rotation wise, 1, 2, 3, 4, 1, 2, 3, 4. 1 goes to 1, 2 goes to 4, 3 goes to 3, 4 goes to 2. Okay. So any other things that you can think of? Any other symmetries? Any other symmetries? Okay, you can check that you cannot have any other symmetry. So what we had basically all the symmetries. We call it D4, dihedral group on equilateral, sorry, on a square. So the number of sides are 4, That's why I put it 4. So note that if you read Dummit Foote book, then Dummit Foote, it mentioned about 8. Why 8? Because just now you'll able to understand, except for Dummit Foote, for most of the books, they consider the base equilateral or the base regular polygon on which you are finding the symmetries. So here the symmetries are looked upon the diagonals on the square. That means it has actually 4 sides, right? So that's why here n equal to 4. That's why we call it D4. And what are the things? E was there, then rotation, rotation square, rotation cube. But if you put r to the power 4, then you can understand it becomes E. Then you had F1, F2, F3, and F4. Now you can check on your own. Okay, take any one of them as F. Say F1 is my F. Okay, then you can check that F2, F3, F4 could be one of this. Like if I consider F, then if I consider RF, R square F, R cube F, then you will find that some in connection is there. So maybe RF, maybe R4, R square F, maybe F3, R cube F, maybe F2, and so on. So that you can check. For example, let's have a look at this, say RF. Okay, so RF with my 1, 2, 3, 4. Okay, that means F. What was my F? F1 was my F. What is my F1? F1 is my this. About this axis is my F1. Okay, so let's check what is my F1. F1 is my this. Okay, so R of F means you just flip it with respect to this. That means here it will 2, here it will 3, here it will 1, it will 4. And if I rotate it, then that becomes 3, 2, 1, 4. Just have a look at 3, 2, 1, 4, and that is F3. So RF is nothing but my F3. So now RF is my F3. Just now I told you. Similarly, if I consider R square F, you will find something like this. So R square F means R of RF, and that is again another rotation of the same thing. That is here 4, 3, 2, 1, and 4, 3, 2, 1 is 4, 3, 2, 1. Let's see which one is your. Yes, 4321. Let's see 4321 where it is. Yeah, 4321. That is nothing but your F2. So this is your F2. So R square F is your F2. So R cube F, it will be your F4. So at the end, what you get basically? You get basically, so D4 is nothing but my E, R square, R cube, F, RF, R square F, R cube F. And what are the relation? R to the power 4 equal to E equal to F square, and R cube F equal to F of R. That you can also check. R cube of F equal to F R. That you can check. So that is the relation. Just now F D3. So we had already D3 equal to S3. We exactly the same way we did. Similarly, if you take it D5, then you will have 10 elements. Now you see that there are 1, 2, 3, 4, 5, 6, 7, 8 elements. That's why Dummit Foote, instead of D4, Dummit Foote use it for D8. But most of the books, they consider D4. That means on 4 regular polygon, you are finding all possible symmetries, and this is the relation. Okay, and you can understand that this is a non-commutative group. And now your homework will be, what is the relation between D4 and S4? Relation between, find the relation between, find the relation between D4 and S4. Now you can check for each of these symmetries I have a permutation, and each of this permutation belongs to S4. Now what is the relation between D4 and S4? Whether D4 is a subgroup of S4 or not? That's the question. Okay. So till now, any question or any comments if you have, then you are free to ask me.